Hi everybody, here is video 4-10 for AP Calculus, and we're in the second packet now. So this is the part 2 packet. It's also green. And there's no homework packet to go along with this. There will be no homework for the rest of the unit. There's only 3 more videos. Okay, so we're on page 3, which is like the first page, in packet number 2, video 4-10 for Wednesday, 12/14. And this is off a day from the calendar that's on the inside cover of this packet, so don't worry about it. But I had to postpone the video watching. So there'll be no homework with this. We're going to first write down Susan's table, and you might have to pause the video to do that because I'm just going to keep talking. And so the new stuff today is that we're going to be doing particle motion. So we'll be, given a situation where there's a particle moving, usually along either a horizontal path or a vertical path, and we'll be given a position function which tells you the position. So imagine, the easiest way is to imagine the particle moving along a number line. So the position function will give us its position on, let's say, a number line. And it could be a horizontal or vertical number line. The first derivative of the position function is the velocity of the particle. And the second derivative of the position function is the acceleration of the particle. And it's important to note that acceleration, so velocity is the rate of change of position, acceleration is the rate of change of velocity. Okay, and so Susan's table is really going to help us figure out a lot of problems. So let's first get some facts out of the way, and all of these facts are included in your flashcards that I sent you and that you should be studying now, leading up to the test. Okay, so motion facts, these are things to know. A particle is moving right or up, those would be positive directions, when its velocity is greater than 0, so positive. Positive velocity means the particle is moving in a positive direction. Particle moves left or down when the velocity is negative. A particle changes direction when V changes sign, and a particle is at rest when the velocity is 0. Okay, and I'm looking at my notes that I did earlier, and in my notes I have V of t. You don't have to write V of t if you don't want, but velocity will be some function of time. Okay, so speed. Speed is the absolute value of velocity. Velocity and speed are not the same thing, because those of you in physics probably already know this, but velocity is a directed vector or something. It has direction. So if it's positive or negative, that tells you what direction you're going. And speed alone does not tell you. If I'm going 70 miles per hour, that says nothing about the direction I'm going in. Okay, so speed does not have direction, but velocity does. So speed, I'll call it S of t here, is equal to the absolute value of velocity. Okay? Now, acceleration facts. Acceleration is the rate of change of velocity. The acceleration-velocity sign pairs at a given moment will tell you if the particle is speeding up or slowing down at that moment. So what I would like you to do here, so the first two are about speeding up, and I just want to be clear. Speeding up means that the speed is increasing. Okay, and slowing down would mean the speed is decreasing. Okay, so please write that in your notes, because that decreasing, I think, will be helpful in some partner problems that are coming up. So guys, basically, if the velocity and acceleration have the same sign, that means the particle is speeding up. If they have opposite signs, that means it's slowing down. And when we're in class together, I'm going to show you graphically what that looks like, because I think it'll help it stick more. So I'm not going to do of t. I'm just going to use v and a for velocity and acceleration. But they are both functions of time. So you could represent them v of t or a of t. So speeding up when velocity is greater than 0 and acceleration is greater than 0. So that's one situation where they could have the same sign. They're both positive. But another situation is they could both be negative and the particle would still be speeding up, because as long as the velocity and acceleration have the same signs, the particle is speeding up. So here's two cases where the particle's speeding up. Slowing down would just mean that they have opposite signs. So case 1, velocity is positive and acceleration's negative. Case 2, velocity is negative and acceleration is positive. Okay, and really, guys, if it seems like I'm throwing a lot at you, it's just because your brain's probably processing like what means what. So the sooner you memorize this information, the easier this is going to be. Okay, so I definitely would get to work on that, on memorizing. Alrighty, so particle motion. A particle moves along a line so that its position at any time t greater than or equal to 0 is given by the function s of t. Now, I used s for speed on the previous page, but in this example, s of t is the position. Okay, so that would be the position function. Okay, right there, where s is measured in meters and t is measured in seconds. So A, find the average velocity on 2 to 6. Guys, velocity is the rate of change of something that's like moving. So velocity is the rate of change. So average velocity, they're asking for average rate of change. So you're really just going to have to know your facts and vocabulary to do these problems. It's really nothing that we haven't done before. It's just like a different context. Now, I would write very small if I were you. I ran out of room when I was practicing this. But okay, so we need the average rate of change of the position function on that interval. So we're just going to go s of 6 minus s of 2 all over 6 minus 2. And I did this earlier, so I'm just going to go fast and say what I got. I got 12. Now, what's changing? The position. The position's measured in meters. It's changing over time, so this is meters per second, right? Yes. Meters per second. So that was A. B. And by the way, you know, I plugged these into the function to get this value. And if I mess up, please comment underneath. Okay, so that everybody knows. So B, find the velocity at t equals 6. Guys, they're not saying average velocity. This is velocity. So here, the velocity is the instantaneous rate of change. It's the first derivative. Assuming that the particle is moving along a horizontal line, in what direction is the particle moving at this instant? Explain. Okay, so for B, okay, so the velocity function is going to be the first derivative of the position function, which is 3t squared minus 12t plus 8. All right. And they want the velocity at t equals 6, so I just plug 6 in for t. And when I did this earlier, I got 44 meters per second. Okay. Now, it's asking, you know, assuming we're moving along a horizontal line, in what direction is the particle moving at this instant? Well, if we've got, so flipping to the other page, so we'd be moving up or right if the velocity was positive. We'd be moving down or left if the velocity was negative. We're on a horizontal path, so that'd be right and left. The velocity is positive. So I'm going to say moving, I'll just say moving right. Okay, I should use more complete sentences, but the particle's moving right, so I'll say moving right. And then we'll say because v of 6 is greater than 0. Okay, so moving right because v of 6 is greater than 0. Part C. Find the average acceleration of the particle on 2 to 6. Guys, acceleration is a second derivative. So acceleration is the second derivative of the position function, but it's also the first derivative of the velocity function. So acceleration, that's the rate of change. Maybe you do this for your notes. Okay, I know it's a little messy, but this is the rate of change of velocity. So they want the average rate of change of the velocity. Well, when we wanted the average rate of change of position, we just, used this average rate of change formula with the position function. Now I want the average rate of change of velocity, so I'll use the average rate of change formula with the velocity function. So I'm going to have v of 6 minus v of 2 all over 6 minus 2. And I ended up with 12. Now the units, if you're in physics, you probably already know this, but the units are kind of funny for the second derivative or for acceleration, because up here it was meters per second, because these values were changing in meters, and these bottom values, these are seconds. So we had the change in meters over the change in seconds, so meters per second. Now, well, how is velocity measured? What are the units on velocity? The units on velocity here are meters per second. So the numerator is changing in meters per second, and the denominator is changing again in seconds. So this is meters per second per second. All right, that's the units on the rate of change there. And the way that this is written, this is just notation, meters per second squared. But if you wanted to say meters per second, that's fine. But it's convention to write it like that. Okay, so that was part C. Part D, find the acceleration of the particle at t equals 6. At this moment, is the particle speeding up or slowing down? Explain. Okay, so acceleration, they're not saying average acceleration, they're saying acceleration. So this is the derivative. So I'll go D, and acceleration, that's the second derivative of s, or you could do the first derivative of the velocity. That's what I'm going to do. Okay, so I get that the acceleration function is 6t minus 12. All right, and so they're asking for the acceleration at 6, and it is 24, and then it's meters per second, so it's meters per second squared. And now it's asking, at this moment, is the particle speeding up or slowing down? Explain. Well, back to the front, we will be speeding up under two cases, if both v and a are positive or if both v and a are negative. So if they have the same sign, then we're speeding up. So I will say, all right, so this, so I will say speeding up. So I'll say speeding up because a of 6 is greater than 0 and v of 6 is greater than 0. Okay, so they have the same sign. All right, so that was part D. Part E, at what time or times is the particle at rest? So really, guys, I'm throwing everything from the first page at you. So when is the particle at rest? Particle is at rest when the velocity is 0. Okay. So I'm going to figure out when that is. So I'll take my velocity function. All right, so I want v of t to equal 0. So 3t squared minus 12t plus 8 equals 0. This doesn't factor, so you have to use the quadratic formula. And when you do that, you end up with, what did I end up with? I ended up with, I ended up with t equals 12 plus or minus. It should be plus or minus, but we can't have negative time, so just plus radical 48 over 6 seconds. All right. Okay, so at, okay, all right, E. Now for F, find the velocity of the particle when its acceleration is 30, I want to change this actually. I mean for this to be 3. I mean for that to be 3. When its acceleration is 3 meters per second squared. At this moment, is the particle speeding up or slowing down? Explain. So we're almost done. So this is for F. So I want when its acceleration is 3. So I'm going to take my acceleration function. I'm going to equal it to 3. And then we get at t equals 2.5 seconds. 2.5 seconds. All right, that's only part of the answer. Now, I'll go like here. Okay, so that's only part of the answer. Now I have to say at this moment, at 2.5 seconds, is the particle speeding up or slowing down? Explain. Well, I know that at, okay, so I know that A of 2.5 equals 3. All right, so I know this already. Now it's going to be speeding up. Back to the front, the particle will be speeding up if my velocity has the same sign as my acceleration. My acceleration is positive, so I need a positive velocity. But if the velocity is negative, then I'd have one of these cases, and then it would be decreasing. All right, so what I have to do is take 2.5, plug it back into the velocity function, which I already did earlier, and I got negative 3.25 meters per second. All right, so I'm going to say slowing down because A of 2.5, the acceleration at 2.5 is greater than 0, and the velocity at 2.5 is less than 0. Okay, that was a lot to fit in there. Okay, we are almost done. Okay, number 2. Refer to the velocity graph below to answer the following questions. Okay, so this is velocity. The y-coordinate of the point gives you the velocity in meters per second, and this is time in seconds. So, for example, at 5 seconds, okay, at 5 seconds, my velocity is negative 3 meters per second. So, let's see, what do I know then? I know that I am traveling in a negative direction, so either down or left, depending on whether my path is vertical or horizontal. I'm traveling in a negative direction at 3 meters per second. Okay, so that's how that graph works. Now we're going to find all these things. If you feel like you've got this, please just go ahead of me or speed up the video. Refer to the velocity graph. All right. Find the average acceleration on 6 to 14. Okay, so average acceleration, this is the rate of change of velocity. So we need the average rate of change, we need the slope of the secant line on the velocity graph, and this is the velocity graph. Okay, so from 6 to 14 seconds. So let's say that there's 6 seconds, there's 14 seconds. So average rate of change is the slope of the secant line. And then we just go like this. There's the secant line, and its slope is going to be the average rate of change on that interval. So for part A, also write small again, guys. Take a moment to digest this if you need to, but we have the average acceleration is equal to negative 3/4 meters per second, so meters per second squared. All right, so that's the average acceleration. At what times is the particle at rest? The particle's at rest when its velocity is 0. This is the velocity graph. So it's going to be at rest where the graph is 0, where it's hitting the x-axis. So for part B, I'm going to say v of t equals 0 at these times: 2, 6, 12.5, and 19. Okay, C. Assuming that the particle is moving along a vertical path, at what time or times is the particle moving up? Okay, so the particle is going to be moving in a positive direction, right or up, when velocity is greater than 0. We are looking at the velocity graph. If the graph is greater than 0 when it's above the x-axis. So it's moving up when the graph is positive, because this is the velocity graph. So from 6 to 12.5, and then I'll say because v of t is greater than 0. Okay, on this interval. D, at what times does the particle change direction? Explain. Okay, so the particle is going to change direction when the velocity changes sign. Okay, and this, guys, should be ringing a bell because we've been looking for sign changes and stuff like this all along. This is the same thing we've been doing, just like in with different words. So I'm looking for sign changes. And am I asking you to explain? Yes. Okay, so for part D, I have at t equals 6 and 12.5, because v of t, I'll just say, changes sign. All right? And finally, at what time does the particle reach its maximum speed? All right, so speed, remember, is the absolute, let me section that off, is the absolute value of velocity. All right, guys, and just bear with me. Oh, this is another long video, but I really, there's no way to go fast, really. Okay. 2, I'm going as fast as I can. So, never mind, I won't do that. To get the absolute value, this is the velocity graph, okay? The absolute value, guys, is always positive. So to get the absolute value of this graph, I'm going to keep the positive part, okay? So I'm going to keep all this. All right, so I'm trying to get the speed graph from the velocity graph. I'm keeping that red part, okay? And now watch this. I made this at school today. And now, so here's the rest. I'm using a transparency. So there's my graph. To take the absolute value of a graph, guys, you just take the negative parts and reflect them over the x-axis so that they become positive. So this was the velocity graph. And now I take the absolute value of velocity and I get speed. So if I go like this, that is the speed graph, the red. The red is the speed graph. And when does the speed reach a maximum? You see way up here. So it was a minimum on the velocity graph, but it's a maximum on the speed graph. Okay. So, and where is this happening? It's happening at 14 seconds. All right. So I was going to do a demo in the calculator with you just a moment ago, but then the video's long, so I decided against it. So that was the velocity graph. Okay. Speed is the absolute value of velocity, so I just flip the negative part of the graph over, and the red is the speed graph. Okay, so you can see very clearly at 14 seconds the speed is the greatest. So part E, I'll say speed equals absolute value of velocity. Which is at its absolute maximum at t equals 14 seconds. Yeah, I mean, I think that's good. Okay. Because I'll say because this is where the graph of the absolute value of t, or I'm sorry, the absolute value of velocity reaches its maximum, I'll say height. Alrighty guys, well this is rivaling the 28-minute video, so I'm sorry about that, but there's a lot going on here and this is just what it takes. So I will see you tomorrow. Bye-bye.